And you see, okay, now it's being recorded, press pound.
Okay.
And if sometimes in here, if it's on mute, automatically mute. So now let's try to send PC again.
Yes.
Because it's not.
Sending content.
Okay, it's on the
Okay,
far
so,
one.
yeah. Okay.
Right. And
Should-
so then if you want to shift where the PC is, you can actually change rear display, right display, left display.
Mhm.
But you should always also be sending through video conferencing. If you're never quite sure if it's going through video conference, then hit computers,
Mhm.
PC, and they can see that. But if you do
Okay.
video conference, then you can sort of
Yes.
change what is on the different screens if you want to change it.
Okay. So you mean, oh, you mean like the screen they see on Zoom?
Video. Well, actually, what they see
Uh-huh. What
is
is
video
video
conference.
conference?
And what we see in here, for example, you know, you can change it to like all or video conference, right, left to take things off. But usually your slides are always on the right.
Always on the right.
But if you want to modify what you have,
Mhm.
you can modify it. But if you're never quite sure what they're seeing,
Mhm.
computers, PC, and then video conference. So you can play with that. And if it's
Okay.
too loud in here, this is the internal volume. This volume is the outgoing volume, you know, what they hear.
Okay.
And it should never
Yes.
go really high because otherwise you get a lot of reverb.
Okay. So that's actually the microphone, the volume.
That's, yeah,
from here.
what's being pushed out.
So
And
that's,
this is just what we
that's
hear
what
too.
we hear. That's
Right,
what they
right,
hear. And
right.
this is mute us, right?
Right, but I'd
Okay.
always double check because there's other ways to mute too.
Okay.
Because it doesn't always work.
Okay.
So anyways, I'll let you go.
Ah,
So
okay.
you're-
Well, thank you so much.
I think it's hours of time.
Yeah. Did you compare? Hi, Professor.
Well, don't call me professor. I'm just like you.
No, you will be a professor one day.
Well, thank you.
Today you are our professor.
How many Zoom students? You do know that? Uh-huh.
William.
I don't know. I don't.
Oh, never mind.
I was going to say a couple of things first about that homework and the
Yes.
projects.
Yeah, sure.
Maybe go and again jump in. Yeah, it's okay. Okay, good morning, everyone. I think we're going to go ahead and get started. Hope everyone had a very nice weekend. Today we have a special treat. So today Young Chow is going to be giving a lecture on logistic regression. I'll be chiming in here and there, but he's going to be leading the lecture overall. So, and just to kind of preview this week, today is going to be a lecture on logistic regression, and then Wednesday we're going to have the lab session since we don't have class on Friday. Okay, so no class on Friday. No need to come in or anything. July 4th is the party at my house. And again, we'll be in touch about transportation and everything like that, but just class Monday and Wednesday this week. And we'll have the lab early on Wednesday. Okay, couple comments about the drafts of the final project. So I'm through almost all of them. I've got 2 or 3 left to read, but everything's looked really good so far. Just a couple general comments that came up repeatedly as I'm giving you feedback. At the end of your introduction, remember just to summarize the overall objectives of your project. So some of you were just providing the literature review and then closing it right there and jumping right into data and methods. Just give the reader a sense of really what your overall goals are, kind of like that prospectus paragraph. Say a little bit about your target population, what data set you'll be using, but just say, here's the overall objective of this paper. This is what we want to do. Then you can transition into data and methods. So that was one common comment. Another one was just simply proofreading. Some of the submissions were a little bit hard to read just because there were a litany of typos and grammatical errors. Like, I know this is just a draft and that's fine, but as you're getting farther along with the paper, especially those of you who have bigger teams, make sure that you have multiple eyes on the paper and that you're proofreading just to clean up those kinds of silly typos and everything. Just makes it easier for everybody to read it through. Last comment, in the statistical analysis portions of your methodological plan, make sure to talk about estimation methods and variance estimation methods. I think that was another pretty common comment, is that nothing was being said about what techniques you want to use to estimate variance. Okay, so whether you're using a replication technique or whether you're using linearization, just make that clear and then indicate what software procedures you're going to be using to actually implement that method of variance estimation. Okay, so provide specifics about the software procedures you want to use and what specific methods you'll be using. Okay, so that was another kind of common comment that I'm seeing. One that came up a couple times, but not as often, there were some general comments about using the logit transform to form all of your confidence intervals. Okay, remember our discussion of the logit transformation was in the context of proportions, confidence intervals proportions. We're not talking about confidence intervals for regression coefficients or means or other types of quantities. That technique, that logit transform technique, and the others that we discussed, specific to proportions. So you're welcome to say that you're going to use one of those transformed intervals for your proportions, but you don't want to say that for other quantities, like your regression coefficients and so forth. So that came up on a couple of the submissions. But overall, everybody's done a nice job getting the structure down, setting up the kind of previewing what analyses you're going to do. I was very happy reading through those. So a couple more I got to read through. I will do my best to do that today, and then we'll continue to move forward with the projects. Okay. Homework number 4 is due today, or was due today. So we'll get back on that this week and hopefully finish that up by the holiday on Thursday. And homework number 5 has now been released. So I wanted to talk about what homework number 5 is asking for. This is the last homework. So we're only going to have 5 homeworks. After this one is done, the rest of the class is just going to be dedicated to making progress on the final project. Okay, so this is the final homework. You also have 9 days to work on it, given the holidays. So the homework's not going to be due until July 10th. Okay, so you have a little bit extra time to keep working on it. So the entire assignment is dedicated to more practice with logistic regression. So homework number 4 was for linear regression. This assignment is dedicated to giving you more practice in logistic regression. And I want to say a little bit about the parts that you're being asked to complete. First of all, exercise 8.2 in ASDA at the end. So this is, again, looking at an analysis of the ESS6 Russian Federation data set. And now we're modeling a dependent variable that represents high satisfaction with life. So we've recoded this variable on a previous homework assignment, but that's now our binary dependent variable in this particular data set, where 1 means that you have high satisfaction, 0 means otherwise. And you're going to use age, gender, an indicator of being in very good health, and marital status as potential predictors of that variable indicating high satisfaction with life. Okay, so for 8.2, as it says in the assignment, only do parts A through F. Okay, so don't do part G of that problem, just do parts A through F of that particular problem. Part A is just to do the recode itself, being careful with missing data on that variable. So you've actually already worked on that for a previous assignment. Part B is to basically code your predictor variables and answer a few questions about the distributions of those predictor variables. Part C is using models that fully account for the complex sample design and the survey weight. Start with bivariate tests of the associations of each of the predictors with that high satisfaction with life variable. Okay, so you're going to look at age, gender, marital status, and being in good health. And then it says prepare a table similar to table 8.5 in the chapter and identify which of those predictors might get some serious consideration given their significance level being less than 0.25. Okay, so that's just looking at bivariate models, looking at the individual relationships of each of those. And then part D says fit a preliminary model with the predictors that you might retain from part C following that criterion. And again, make sure to use the design variables and the survey weight for variance estimation. And then based on these results, what predictors will you retain for the final model? Okay, when you're fitting that full model, does everything still seem to be important? All right. Part E then says, think about two-way interactions of very good health with each additional predictor in your final model. So for part E, even if some of those other predictors were not significant, you still want to include them to specify the interaction. All right, so keep that in mind for testing the interactions. We want to make sure those lower order terms are included in the model as well. And then prepare a table similar to table 8.9 to include your estimated coefficients in that model and make a decision about whether you want to retain those two-way interactions. So test those interactions, see which of them should be retained in the overall model. And then part F is really speaking to the interpretation. So based on the final model that you're presenting here from that model building process, describe the results and interpret the estimated coefficients for each predictor. Okay, so make sure you get the interpretation down for each of those different predictors. And then discuss the overall approach that you use to incorporate the complex sample design features. Okay, so you're going to summarize the interpretation of your results and then talk about the approach that you use, again, being specific about the estimation method and the method of estimating variance. Okay, so that's related to the comment I was making on the final projects. Okay, so that's parts A through F, that's building that model and then ultimately presenting and interpreting those results. All right, the second problem on the assignment is then exercise 8.4. So this is again speaking to the interpretation of a logistic regression model that includes a significant interaction term. Okay, so for this particular problem, 8.4, you're given estimated coefficients for a model that included an interaction between age and gender, okay, in predicting this indicator of having a lifetime diagnosis of alcohol dependence. So you're actually given the output. You don't have to actually do any analysis in this particular case. But part A says, again, look at the general estimates that you see from that table. And then part B says, based on what you see in part A, prepare a short paragraph that interprets the results provided. So it's just additional practice in interpreting the estimated coefficients in a model that includes an interaction term. Okay, so you're going to get two opportunities to practice with how you would interpret estimated coefficients representing interactions in the context of logistic regression, just because this technique is so incredibly important when we're analyzing survey data. Okay, so that's part 8.4 is interpreting the interaction that you see there. Okay, and that's the assignment. So any questions about what this assignment is asking for, due dates, logistics, anything else like that? Pretty good? Okay, so again, oh, yep, Jones? Yeah.
Are we restricted to a particular software?
No, again, you're not doing any analysis. So 8.4, you don't have to do any analysis. You're just taking what's provided in that table and interpreting the results. That's all. Yep, so you don't have to do any analysis for 8.4. Okay. Yep.
I have a general question there. Can we run models simultaneously? One for regression, one for ratio.
What do you mean by regression and ratio?
Run single regression by regress X. And the other one is the ratio estimate.
No, yeah, not for this. This is logistic regression. So I don't know what you mean by ratio estimator in this context.
More in this context, in simple linear regression.
Oh, I'm sorry, I didn't know you were asking about linear. Okay, go ahead.
Yeah, so can we run simultaneously for the comparison ratio and regression comparison?
You could, but again, if you're comparing those models, you have to make sure that you're talking about the exact same coefficient, right? So ratio estimator has more of a descriptive focus in estimation. And regression, your interest is in relationships. So thinking about comparing apples to apples there, are you really doing that? Or are you comparing a descriptive quantity to an estimated relationship? So you just have to make sure that you're looking at the same interpretation both ways. If not, it doesn't really make sense to compare them. Okay, any questions about this specific assignment? Homework assignment number 5. Sorry, Newman, I was a little bit confused. Any questions about this assignment? Okay, more general questions about linear regression or anything else before we get into today's lecture with Young Chow? Any general questions? Everybody's good on logistics, everything else. If you have questions about any of my feedback on the drafts, please send me an email. Okay, don't just struggle in silence. If one of my comments wasn't clear, you're not sure what the next steps are, send me an email if you need clarification or anything. More than happy to correspond and even meet with you about that if necessary. Okay, if there are no further questions, I will turn it over to Young Chow and he's going to walk us through logistic regression. And I may interrupt him here and there, but I'll let him do most of it. So. Okay, thanks everybody.
Thank you, Brady. All right. So today I'm going to give you a lecture on logistic regression. How many of you have learned this before? Well, many of you. Well, I'm glad. And if I were wrong about something, just correct me. I've learned this 10 years ago, so remind me of something. Yeah. All right. So logistic regression. Why are we doing this? Well, the dependent variable is a binary variable, or which is often happen in survey, a yes/no question. For example, this question, whether you are satisfied with your life. It's a yes/no question. And if I plot this variable against age, can you draw a line, a regression line through this figure to get a linear relationship between these two variables? It's not that straightforward, right? So rather than predicting these two values, yes or no, we try to model the probabilities that the dependent variable takes one of these values. And how do we do that? If we just consider this linear regression, if we just run a linear regression on this binary variable, we are actually modeling the conditional probability of being satisfied with life, given the predictors we have. For example, you can also predict conditional probability of not satisfied with life, but that's your choice. Yes, no, you can change the coding. And there's a problem with that because the probability must be between 0 and 1. A linear predictors on the right-hand side of this formula, it can take any real number. It's unbounded in theory, although in reality you wouldn't find a variable or like age has a range. You wouldn't find a variable range from negative infinity to positive infinity, but in theory it's unbounded. But on the left-hand side of this formula, the probability is bounded between 0 and 1. So there's a problem. that problem will cause the prediction of the probability lies outside the range 0 and 1. You may have a negative probability prediction or probability larger than 1 in your linear model. And there's a solution which is to transform the probability to remove that range restriction and model that transformation as a linear function of the covariates. So we do some magic to transform this probability to remove the range, to make the range from between 0 and 1 to from negative infinity to positive infinity. How do we do that? So we move from the probability to the odds. Odds, I don't know if you're familiar with this way of expressing probability events. Well, actually, I don't quite get it. But if you ever do sports betting or gambling stuff, probably you have heard this term very often in casinos. Yeah, but I don't know. Yeah. So the odds actually is a ratio between an event happens and the event not happen. So, for example, the probability of having a satisfied life given the covariates divided by the probability of not having a satisfied life. So that's kind of something happened, the ratio of something happened divided by something not going to happen. So that's, and this odds, it has a range from 0 to infinity. The next step, we're going to take logarithms to move from odds to log odds. If we take a logarithm of these odds, we will get the range from the negative infinity to positive infinity. So this is a logistic regression function. So this is a logic function. It's a function of the probability. And after we do this transformation, we have the range on the left-hand side of this regression equation equal to the range of the right-hand side of the regression equations. And this logarithmic transformation, you can transform this back to the probability. It actually maps the probabilities from range 0, 1 to the entire real line, and the probability can be solved from the logic model. You can back out the probability. So that's somebody came up with this transformation, was a smart person. Yes, Sarah?
No comment. Okay.
Yeah.
Sorry, Sarah, do you have a question or?
No, I don't. Sorry.
Okay, yeah, never mind, yeah. All right, so now you understand where do we, yes.
I want to add just one point here. So notice in the transformation that Young-Chao is using here, there's no residual in the expression of that logistic regression model. Everybody see there's no E there? Why is that? Anybody say why there's no leftover random variation when we're modeling a binary dependent variable? Do we have a thought on that? Here.
Maybe because it's either 0 or 1.
Well, you could get a residual if you were using the approach Young-Chao initially said, and you just fit kind of a naive ordinary least squares, you'd still have a residual there. But in this specification, where we're modeling the probability, what defines the variance of a binary dependent variable? What's the variance of just a simple 1, 0 variable? Exactly. So the variance is entirely defined by pi. Once we know pi, we know what that leftover variance is. Okay? So there's not that in the first formulation of this model, there's not that leftover residual. So that's another common issue when people are writing down these models, is that you add that residual, but that variance is defined entirely by whatever that prediction of pi is based on the model, because we're dealing with a binary dependent variable. So knowing pi already defines that variance. We don't need that additional residual. So when you're writing these models, the way Young Chao has written it here in the middle line, that's how you would write these models. We don't include that additional residual that we saw in linear regression. So it's an important thing to recognize here is that the variance is defined by the mean, and that's common to many of these kinds of generalized.
Yes. So, well, we will also come back to that point later to expand that point. Yes, you will be careful. When we have a linear regression, we have a residual, we can have a residual here. But when we have a logistic regression, just note, because this is a place usually people have a mistake here. So yes. All right. So yes, here. So since we have a binary dependent variable, which takes value 0, 1, 1, and this kind of variable, we usually assume it follows a binomial distribution. The expectation, the mean of this kind of random variable is n times the probability, and the variance of that random variable is also a function of the probability. So this is what exactly is Brady said. So the mean and variance depend on the underlying probability pi. So any covariance that affects the probability also affects the mean and the variance. So that what does that mean? So your variance depends on the x. So you don't have almost the statistical assumption hold here. Assumptions violated. You cannot use least squares estimation in logistic regressions. So we're going to turn to maximum likelihood estimation to estimate the logistic regression model.
Does anybody use linear probability models in their work? Or you just use OLS to model a binary variable? I get into a lot of debates with people about using linear probability models. They think it gives you a probability, everything's easy to interpret. You talk about the change in the probability. But remember, all those assumptions that we made about least squares, by definition, for these models, they're violated. So all of your inference does not, like, it's not really valid inference based on the assumptions that we're making about least squares. This is another thing that people kind of forget about is those underlying assumptions. Sarah, could you mute yourself, please?
Yeah.
Okay, please mute yourself. So this is another very important point. Whenever you're reporting inferences based on that kind of simple ordinary least squares model for a binary dependent variable, think about whether all those assumptions that we discussed are valid. This is something very important to think about. Least squares just is not appropriate in general for these types of models.
Yes. So what we were doing, the logistic regression, so it's kind of the process. We generalize the linear model to the case where the dependent variable is not a continuous variable. So what we usually call this kind of model generalized linear model. And this kind of model has 3 components. These 3 components I have shown you in the previous slides, like the distribution of dependent variable. You need to choose a distribution of the dependent variable. That distribution will determine the mean and the variance. And the linear predictor, which is the thing on the right-hand side of the regression formula, the predictors you've chosen. And there's a link function to link these 2 stuff. So like it's a transformation that describes how the mean of the dependent variable is related to the linear predictor. And in the logistic regression, we use a logic transformation. which you have seen in the previous slides. And there are other transformations you can use, like Probit transformations. I think this transformation is often used by economists. They like to use this Probit model. And complementary log-log transformation. And I think this, if I remember correctly, when you have the probability close to 1 or 0, this may be suitable. And here's a comparison of these 3 link function. So you see they all S-curve-like transformations. So they're sort of similar. So you're probably gonna pick one of them according to your needs. And here today we just focus on logistic regression. And actually the linear model is also a special case of generalized linear models. The link function for the linear regression is an identity function, which means you do nothing with the mean of the dependent variable. You don't have to transform it. So, as I said before, you cannot use least square estimation. Now, how would you estimate the logistic regression model? We use maximum likelihood estimation. So the maximum likelihood estimation, we first need to write a likelihood function for your data. Here we consider a simple random sampling of cases. So here's for example, for a simple random sampling of n independent binomial observations, the likelihood function is the product of the probabilities of observing the data given the parameters. So what does it mean? It's like given the parameters, what is the most probable parameters that can make us observe the data? We have this is a likelihood of observing the data. We want to maximize this likelihood of observing data to solve for the beta, solve for the parameters. We want to get the parameters that can, you have the data, what is the beta that can make this data most probable? So we do that by some mathematical calculations. We estimate the parameters by taking the first derivative of the log of this likelihood function with respect to each parameter and set them to 0 and solve for those parameters. Well, I think I could do that by hands 10 years ago, but nowadays I think I have lost my hands. Well, you don't have to do that manually. Software will do that for you, estimating the parameters. And actually no closed form solution, no analytical solution. So the iterative methods like Newton-Raphson algorithms are used to estimate the parameters. And after estimating the parameters, you will need to estimate the variance of the parameter estimates. And then you take the second derivative of this log likelihood function with respect to each parameter, evaluating at the maximum likelihood estimate you have in the first step, and invert that to obtain the variance covariance matrix to get the variance of the parameter estimates. When you get the variance of the parameter estimates, you can construct confidence interval with that. This maximum likelihood estimation is used only under simple random sampling. Why? Because under complex sampling, it's not appropriate because the probability of selection is not constant across observations. So it's not everyone is equally selected into your sample. And another violation is that the observations are not independent. So when we use maximum likelihood estimation, we assume that we have an independent binomial observations, but under complex sampling, due to clustering or stratification, those observations, they are not independent to each other. I'm sorry.
Cannot use the justification for this case. Cannot use the justification for this case.
Mhm.
Complex sample design. Cannot use justification anymore.
No, if you have complex sampling design, that will affect the estimation of the standard error if you cannot use maximum likelihood estimation.
So in this case, also the solution for the binary outcome by.
Yes, so the solution would be we can use some pseudo maximum likelihood estimation. Yes, so look at this formula, you will see there's a weight over E. I think so and also here we have beta here, the parameter we denoted as beta because I think maybe in the last lecture you have been exposed to the superpopulation model and the finite population. So I think now we restrict ourselves to a finite population. So this is the finite population regression parameters. So we use a pseudo maximum likelihood estimation, and in this way you can incorporate your complex sample design. You can incorporate your weights. And yes.
So right, Aaliyah, if you look back at the previous slide where we assumed independence, right? That independence assumption allowed us to multiply those probabilities for each individual sample case by each other. To say these are independent contributions and we're looking at the overall likelihood of the observed data. So that's what allowed us to simply take those products. We can't write the likelihood in that way if you have clustered data where observations from the same cluster are no longer independent from each other. Right? We literally can't write down the likelihood the same way. So on the next slide, this pseudo maximum likelihood approach, what we're doing in raising each individual's contribution to whatever their weight is, we're saying we're trying to come up with an estimate of what the population likelihood looks like. Where this idea of independent, dependent no longer matters, because we're trying to write down the full population likelihood for everybody in the population, not just the sample and clusters, but everybody in the population. In that case, the notion of dependence due to cluster sampling no longer exists because we have data for everybody in the population. The idea of sampling has gone out the door. So the idea of raising each individual's contribution to the power of their weight, just again, means there's 100 other people like me if my weight is 100. There's 100 contributions of whatever my pi or my 1 minus pi is. That likelihood. So we can write down that likelihood. And all that is an estimate of what the population likelihood actually looks like. We're going to use that same idea for all different kinds of generalized linear models. We're trying to come up with an estimate of what the population likelihood looks like via the use of those weights. So again, when you're ignoring weights, when fitting these kinds of models, you're specifying a likelihood that doesn't even make sense. That's the problem. So that's where this pseudo likelihood comes in very valuable.
So Brad, can I ask a general question?
Yeah.
I'm not very much related to this.
Sure.
So for those who try to estimate a multi-level regression.
What kind of regression?
Multi-level.
Okay.
Would you provide maybe some general comments? Because I think the aim is that they should also account for the nested nature,
yeah,
and maybe clustering. Would you provide some general comment? How do you relate to?
We're gonna provide a whole lecture on that.
Is it?
So Young Chow is gonna provide a whole lecture on that.
Oh, okay.
Yeah, so that it doesn't just deserve comment, it deserves 2 hours. Yeah, so
Okay.
multi-level, it takes this, what we're talking about right now, to a whole different level. Literally.
Okay, thank you.
You're splitting the likelihood into several levels in the data hierarchy, and you need weights for each of those levels. So I'm saying it's taking this basic idea and really expanding. So we gotta get this basic idea down first, and then the multi-level idea will make more sense. Okay, once we have this, but yeah, Jupiter, we're gonna spend a 2-hour lecture on it.
Thank you.
That's just one comment.
All right, thanks, Brady. Yeah. So yes, we'll need to use pseudo maximum likelihood to estimate the model. And to estimate this pseudo maximum likelihood estimation, well, we will follow kind of similar way to estimate. Like we also need to maximize this weighted pseudo likelihood function using iterative methods, as we did in standard maximum likelihood estimation. And when it comes to estimate the variance of the parameter estimates, well, it's more complex. You can pick the Taylor series estimation or replication methods, but replication methods, well, that would be computationally sometimes inefficient, but it's easier. Well, you have to learn this before, yeah. Okay. And when it comes to the test of the model parameters, whether you need to test your hypothesis. So predict whether this is a significant predictors of the outcome of interest, and you want to test the null hypothesis that the parameter of that particular predictors is equal to 0 or not. So what we usually do is do a word test, and that test statistics is a ratio of the parameter you estimate to its standard error. So it's the same here, also under the complex sampling design. But for the complex sampling design, the test statistics, the degrees of freedom, you're going to use the design-based degrees of freedom, which is the number of cluster minus the number of strata. Alternatively, we can also treat this the square of this test statistic, the square of this ratio of parameter estimate to its standard error as a chi-square statistic, and it follows the chi-square distribution with 1 degree of freedom. And the likelihood ratio test is to use to compare the likelihood of the model with the parameter of interest to the likelihood of model without the parameter of interest. It's used to compare models with different parameters. You can include some covariates and not include some covariates and compare the models. And this test statistics, well, I can include the formula here. And this test also follows a chi-square distribution with a difference in the number of parameters between the two models you are comparing. But this is not applicable to complex sample designs. So there's another way to do the model comparison when you have complex samples. We will go to that later. And some regression diagnostic standards. Well, you have seen this before, I assume. The goodness of fit statistics, there are many of them. And the problem is that they are all designed for independent observations. For example, Pearson deviance Osmo-Lemmershul test classification table. You can predict the outcome and classify them. Calculate whether you have how many percent you have correctly classified them, and the area under the ROC curve and pseudo R square. Well, one thing I want to remind you is that pseudo R square is not R square. You have learned in linear regression. It cannot be interpreted as explain percent of the explained variance. It can only be used to compare models. It cannot be interpreted as in a way that, oh, you have with these predictors, 100% of variance in the dependent variable expand. No, in logistic regression, you cannot do that. It's pseudo R squared. Only use that to compare models. And there are actually I think for complex sampling design, you can do something goodness of fit tests in Stata. We'll go to that later. And this is not, I think this is recently developed. So not very common in software. And in R, I don't think it's available in R right now.
Yeah, we'll come back to that. But
Yeah.
the design-based version of Hospital Lemma Show is currently only available in Stata. It's a can option. We'll come back to it.
Yeah.
Yeah, George?
I have a question. So the T statistics, if you square it, that
Mhm.
becomes a sky square.
Mhm.
That's what you're saying.
Yes, so the T statistics, you calculate that as a ratio of your estimate and the standard. So if you square that, that follows the chi-square distribution with the 1 degree of freedom difference, as I mentioned here. Yes, that's an alternative way of viewing this. And you also need to do some test or some visualization to detect the influence and outliers. Or these are some common ways to detect that, as you have done in linear regression. The Cook's distance and matrix, or the change in the chi-square statistics if you delete some cases. So these are the ways they don't change. They can be applied to the logistic regression cases as well. Well, so let's go through some examples. But it's not very much content actually. So yeah, logistic regression is it's straightforward here.
Well, before we get into the examples, anybody have any questions about the concepts? The basic concepts that we're referring to here, and what's different with taking complex sampling? It's the same story with variance estimation. It actually took an entire paper to figure out how to do linearization for generalized linear models, where you don't have a closed formula for the estimator. So that's a really important work by David Binder that was done in the early 1980s. But we now have linearization as an option, these iterative estimates, so that's a good thing. We didn't always. But any general questions about the concepts here before we get into the example?
Okay. Oh, let's go through an example of fitting the logistic regression model. Well, that will give you more direct sense of how it works. So this example is about lifetime major depression prediction. Hopefully taking this course, we will not be a predictor. So we are using the data, the National Comorbidity Survey application. You have that data on Canvas, and the question is to assess the significance of some potential predictors of having lifetime major depression for adults greater than 17 years of age. So the dependent variable is a binary variable here, whether you have lifetime major depression, yes or no. And we have 5 predictors over here. So all these predictors are categorical. Like age is a 4 category, age variable and sex, alcohol dependency, yes or no, and 4 levels of education, and 3 marital status. So
This was another comment that I made to some of you on your projects. When you're listing the predictors that you want to consider in your models, this is what I mean by being clear about what possible values they take. Like some of you in your methods, you just said, I'm going to use age, sex, alcohol dependence, education, marital status as predictors. That's great. Gives me a sense of what you're doing. But to be very explicit, you want to, like we show on this slide, say what are the possible values that every predictor takes. That's what I was getting at. And if it's continuous, just provide a range or something. These are all categories.
yes. So given the variables we have, where before we fit the model, we always want to do some bivariate analysis to see if there's a relationship between these 2 variables. So for example, in R, so I'm showing R code here. So in R, for example, here I'm do a bivariate analysis between the dependent variable and sex. The first step is always to specify your sample design, survey design. You have to done this before. So yeah, you have supplied the strata, cluster, and the weights. And here is a bivariate chi-square test, and you see that here. So for male, 15%, about 15% of males, they have lifetime major depression, and about 22.6% of females have lifetime major depression. And here, this command will give you the raw and Scott adjusted F statistics. And apparently, this is a significant, there's a significant association between this sex and the major lifetime major depression. And before we fit the model, let's do some simple math to understand odds, because we are going to use odds. The log odds is on the left-hand side of that regression equation. So what is odds? So here is the percentage of having lifetime major depression. For males, it's 15%. For females, 22%. So the odds for females having a lifetime major depression, that'll be 15% divided by 1 minus 15%. Something going to happen divided by something not going to happen, the probability. And you have the odds of 0.18, around 0.18 for male. And for female, you do the similar thing, and you have the odds of 0.29. So apparently, the odds of having lifetime major depression for female is higher. And the odds ratio is just the ratio of two odds. So here, if I put like the odds on the numerator, and it's 0.29 divided by 0.18, that odds ratio is around 1.619. So that means the odds of having lifetime major depression are 1.619 times higher for females than for males. Yes, so this is a way to quantify the odds between the odds of having lifetime major depression relatively between male and female. So here's let's fit a simple. Yes.
Sorry, can you go back to something?
Yes.
So just one thing to be very clear on, some people look at an odds ratio, they interpret it like a ratio of probabilities. Don't. It's not a ratio of probabilities, it's not a ratio of likelihoods. We wouldn't say that females are 1.6 times more likely. Okay, that's a probability interpretation, right? An odds ratio is just that, a ratio of odds. Don't make it out to be anything that's not. So when you're interpreting the results of logistic regression, you want to use the exact language that Young Chow is using here. The odds, not the probability, the odds. You look at the ratio of the probabilities, which is what's sometimes called a relative risk. That ratio is very different, 1.619. That's the important thing to recognize.
Yes. So be careful with the interpretation. You have this is ratio of odds, no probability statement here. And next, we're going to fit a simple logistic regression, just with that one single predictor, sex. Yeah. Oh, yes.
So to determine the numerator and the denominator, you always look at the lower ratio.
You mean the numerator and denominator here?
On the reward ratio.
Oh,
yeah,
no,
here.
it doesn't have to be worded that way, Munga. So like if you wanted to look at the comparison of males versus females, you could just look at it. It doesn't have to be higher over lower. It can be whatever contrast you're interested in. And more generally, this is comparing two groups. You could look at the odds ratio for a 1 unit change in a predictor. Like if you had a continuous predictor, where in the numerator you'd have the odds as the predictor is 1 unit higher, and in the denominator you'd have some kind of baseline. So it doesn't have to be higher over lower. You could have an odds ratio below 1 to make sure.
Yes. So we move to the logistic regression. So here's the way you specify a logistic regression under complex sampling design using survey package in R. And here I only have included this sex as a predictor, single predictor. And here's a summary of the model, this simple logistic regression. So we have an estimate of 0.48. So that 0.48, you remember that this is a logistic regression. On the left-hand side of the regression equation, it's logic, it's a log odd. So this 0.48, if you interpret that, how would you interpret that? Anybody has an idea how to interpret that 0.48? In terms of the odds? Log odds, right? Yes. So if this is continuous, it's just the one. If the 1 unit increase in this variable, you have 0.48 increase in the log odds. But here is like this is not continuous. This is a categorical. It's a binary variable. So being in female, being as a female.
Here.
Yes. Yeah.
Can we just? I have a question.
Yeah.
Quickly. Why is it quasi-binomial? Like binomial.
Yes.
The setting.
Yeah, so when
Oh,
you're using SPY, GLM, and R, you have to specify a family. So it's like Young Chow was saying, you have to choose a distribution, you have to choose a link function. Okay. When you specify a family in SPY, GLM, you pick this distribution and then you pick a link function, but there are also default link functions for each of these. It's quasi binomial for the same reason we call it pseudo maximum likelihood. It's because a lot of those weights are decimal weights. So it's not really a binomial observation because you're raising it to the power of something that's not an integer. So that's something that Lumley used to represent the fact that these are weighted. And in fact, if you tried to use binomial and it picked up a decimal weight, the function would complain. That's kind of a head scratcher because people say, oh, I'm fitting a logistic regression. Why isn't binomial working? It's because you have a decimal weight. So the quasi is just saying these are decimal weights in the pseudo likelihood that are approximating this binomial likelihood function. So every GLM is going to have a different family and then a different link. And in parentheses after that family, you can say what the link is. The default for quasi binomial is link equals log, which is the link function that we're using. But you can change that to probe it. I think you can change it to C log log, but there's a default for each of these families. But the quasi has to do with the decimal. Great question.
Yes. So if you fit a probing model, you will change the distribution. So yes. So the logistic regression coefficients, what you have seen, that represent the change in log odds of the dependent variable for when 1 unit increase in the predictor and holding all other variable constant, although in that simple regression, we don't have other variables. So the coefficient for sex is 0.48. And that means that being female, when compared to the reference category, which is male in this case, is associated with the increase in the log odds of having lifetime major depression. And this interpretation is not that straightforward. What is log odds? That's not something people usually say. Odds already odd. Log odds even more odd. So we want to transfer it back to something we're familiar, like odds ratio. So what we do here, we exponentiate the coefficients to obtain the odds ratio. How does that work? So you remember that on the left-hand side is log odds. If we exponentiate that, we get the odds. Here is the odds of female, because we have 1 predictors here, so that x equal to 1, so we have b0 plus b1. And if we exponentiate the right-hand side of the regression equation, we get this one exponentiate of the b1 plus b0 plus b1 for female. If you are a male, the value of x is 0, so you don't have B1 here, so you have B0 when you do the prediction. So when I exponentiate B0, that's the odds of that odds for male. And if we just take a quotient of these two, the ratio of odds for female and odds for male, or if you remember the quotient rule from logarithm, this becomes e to the power of b1 because I skipped one step. Is e to the power of b0 plus b1 divided by e to the power of b0 equal to the e to the power of b0 plus b1 minus b0. If you remember the rule, then it becomes e to the power of b1. E to the power of b1 is you take the exponential of the coefficient for b1, which is this one. You get the odds ratio, and odds ratio here defined as odds of female divided by odds for male.
So see, back to Munga's question, if we change the reference category from gender to be female, we would just get the flip. We calculate the odds ratio, and it would be an odds ratio less. It just depends on what you choose to be the reference.
Yeah. Right. So what will happen if we take a exponentiate of 0.48? So here's our code here. If we take exponential of this coefficient, we get a 1.619, which is exactly the same we have here. So why is that the case? Because we haven't included any other variables in the regression. So this is simple regression, and this is kind of if we include other covariates in the regression model, this may change because you are accounting for the effect from other predictors. And another point I want to mention here is the test here. So you have a t-value here. That's calculated by the estimate divided by the standard error. You get this t-value, and you also have the p-value in the output. So the odds ratio, the interpretation is the same in this case. So what if I include the other variables? I have 5 variables, and now I include all of them in my regression model. I will have a longer regression output. And now if you have spotted here the estimate for female, the sex variable, it becomes 0.57735. It's different from 0.48. So after accounting for other variables, the estimate changes. And again, if we exponentiate these coefficients, the odds ratio now becomes 1.781, and the interpretation is the same here, but you gotta add another statement. You gotta say you are holding all other variables at a fixed value when you have multiple regression. So any questions so far? This is like a quick example of fitting a logistic regression in R. Is that clear? Any questions?
Just who wants to take a shot at the kind of plain English interpretation of like age category 60 plus? Back to again this question. There, that's an odds ratio that's 0.508. So what would our interpretation of that? Do the odds go up, go down? Or what is that telling us about age 60 plus relative to the youngest age?
The odds are about half, right?
right? So remember, it's a ratio of odds. So the odds in the numerator, which in this case would be age 60 plus, divided by the odds in the denominator, which would be the reference category, which is ages 29 and below. That ratio of odds is about 0.5. So it's, the odds are cut in half of having major depression for 60-plus-year-old relative to 29 and below, which kind of matches with our intuition. Some people like to interpret odds ratios on a percentage scale. So if the odds are cut in half, they're reduced by 50%. Or like in the case of female, if the odds are 1.78 times higher, the odds go up by 78%. It's all relative to 1 when you're doing those percentage calculations. So you'll get, again, practice doing that on working 5.
Yes, so you, I think the major task of your, when you do a regression, you want to correctly interpret those coefficients. And remember that you have the standard error. You can construct confidence interval, and you're going to use the same way to transfer it to the odds ratio. You can construct a confidence interval around the odds ratio, just the same way. Exponentiate. And the test of model parameters. So I think I've shown you the test for individual parameters. And I think you have learned how to do test for parameters from a multi-parameter case. And this is how you do this in R. And you probably have known this in a previous lecture, right?
Okay, so main point here, reg term test is available for pretty much any model you're fitting using SQIGO. It just underscores that this is a very general purpose wall test for testing these blocks of predictors. So you can use reg term test given the saved object from any SQIGO. So that's another very handy kind of multi-purpose approach.
It's okay. I think I have finished an example of using R to fit the logistic regression. Yes.
Right. You mentioned earlier that like for testing model parameters, we can use either the Waltz test or the LRT, the declaration test. Are there specific cases where we would prefer the Waltz over the LRT or the LRT over the Waltz?
Yeah, that's a good question. So in reg term test, you might remember from last week, you can choose method Wald or method equals LRT. Lumi wrote a paper addressing what Yang Chao said earlier about how we can't do a likelihood ratio test under SRS assumptions for complex samples. He wrote a paper extending that or addressing that problem for complex samples where he talked about what you need to do for a likelihood ratio test. The big difference still has to do with sample size. So typically the Wald test is going to be preferred if you have a smaller sample size. The likelihood ratio test still assumes a very large sample size. It's approaching the population size. So of the two, especially if you're dealing with a subpopulation here or something like that, where you have a pretty small sample, the Wald test would probably be preferred for smaller samples, because likelihood ratio test still relies on asymptotics to some extent. But both are available. And with a large enough sample, like we saw in the lecture, if you choose either or, it's going to give you very similar. But if some people are kind of committed to a likelihood ratio test, they've used it a lot in prior applications, you can change the method for reg term test to be LRT. And that's a relatively new development, like within the past 10 years. For many years, people just made the statement that Yang Chao was saying and said, well, we don't know how to do it. But then they wrote that paper showing how to do that in a complex sampling case. So they added that functionality to reg term test. Stata only makes the Wald test possible. Stata hasn't yet programmed that Lumi version of the language.
Any other questions so far for the example?
Want to take a break up, Joe?
Oh, yes.
Yeah,
I think
before
we
you
need a
guys
break.
leave. So why don't we break until about 10:15, then we'll come back and talk about the corresponding SCADA.
Okay, great, thanks. How was your
Yeah.
Yeah, but I don't right now, it happens sometimes in the Philippines, yeah, right? I just go to the local. I mean, how do you the way.
Maybe I am wrong. In my case, I so all the is different for you. I think because I use it, this function like was doing that. It's also pretty like.
Oh.
Yeah, right, because I regress is retarded first.
And
then the test. That's probably the reason. It's not, then I don't, it's not.
But I think everything is wrong.
But you know how to do it. It's just that.
Because I don't want to I know. After
What is this?
we're discussing why there are faults.
We're the same. That's not the principle. No, but like,
I know all this.
but
Yes, I know that, but I think. Everything wrong, because everything
No.
is wrong.
the question was using your final model. It doesn't say their final model. So it depends on you. So regardless if you're wrong in the interaction or not, as long as it's
Hello?
your final model, that's what you said, still gonna be okay.
And also,
That's what I read and asked. Yeah, I don't know. I don't think it's a chain question.
there you go.
I know maybe that question misunderstood.
Yeah.
I know that you have helped them, I think.
So I would.
Specialized.
After.
Yeah. Jane questions are good.
That's specialized.
Yeah.
That's how, they.
Yeah, all the software defaults as we talked about.
It
The
doesn't,
software
it
defaults
proves that
using
you know how to get it.
just waiting, it's just a specialized way.
One of them, I think,
Makes it
where
better.
it has changed.
the estimation method is weighted to the least squares. One of those various estimation methods.
I never would have guessed sinus spelling.
Weighting is specialized.
NY something something. And your ID. Yeah, it's so weird.
Yeah, everybody will get it. But it's not for individuals.
I like this. I like
Everybody will get a final grade.
I had a hard time understanding sometimes.
Yeah.
It was old English.
And usually, like.
When people laugh, I just laugh.
But they're acting, their boobs are big, so it's.
Oh, it's okay. Don't worry too much. It's like, it's just it's
But like after going to Barbie, we're just like, better see. Then we'll have to be a oh, haven't done it yet. When you got back from KT.
Yeah, I know, I was like. We can do it today. Okay. Okay, fine. We're not beginning to.
But Maria, maybe.
I mean, yeah. I sent.
Columbia Business School.
Oh,
Is it president? Is it the one who won in 2019? 2019 or now? 2018 or 2021. It's just 2018. Oh, it's
supposed to be yes. And I would say for cigarette, use my watch. Yeah. But the craziness is going. I was going to go.
Okay.
I know that you went so.
We have a nice day.
Right.
Even planning to finish everything.
I think outside, so until right. What do you think? What so today? Individually and then so. So everything. Whatever not. That's it.
All right. So we still have time to go through some data implementation of logistic regression. Well, I haven't been used data for quite a long time. But when I learned logistic regression, I used Stata. After that, I turned to R, and I never came back. So, so yes, I think yeah, I can say I'm quite familiar with this. But I think this Stata command may be more straightforward to you if you are new to R. This is easy. Stata may be easy for you. Yeah, and so using Stata, well, you just did something similar to you have done when fitting the linear model. Just use logic or logistic command, and they have different defaults. So, like for example, if you use logistic command, it defaults to odds ratio output. So, but if you use logic, it defaults log odds output. So that's just the models are same. Models are same, but you just have different outputs. And also there's defaults to the reference category. If you have the categorical variables there, you can change the category for the categorical predictors using some options. And here you can use the test statement. This is the equivalent to the random testing R for the word test of multi-parameter hypothesis. And here is an example to test the null hypothesis that all of the parameters associated with the age predictor are equal to 0. You can use this statement in Stata. And to do some bivariate analysis, you have done this before. Like you first specify the survey design, specify the cluster, specify the weight and the strata, and you do a tabulation between the two variables. You have 5 variables, 5 predictors, and run a model, run a logic model. You specify a survey logic and your dependent variable category, your 5 categorical variables. I don't think it's that hard. Like you have done this for linear regression, similar, just a change of this part. And the word test, I have shown you the test statement. We do the test of multi-parameter predictors.
Anybody have any questions on the code? This is just more of the same point that Stata makes incredibly easy. Just adapt various kinds of models to the design base framework. We're literally just changing the name of the command to fit the different model. And all the other commands are the same. So you're becoming more and more comfortable with how SQI progress is working. Pretty much SQI emojis logistic work exactly the same.
Yes. And in Stata, we have a comment for testing overall Kuna's fit. So this Archer and Lemashow's design adjusted test. So we can call that test by this command. And we will have a design adjusted F statistic. This is I don't remember. Oh, this is a test of the model. Just fit it with the 5 predictors. And in this test, this design adjusted F test statistic is 1.229, and it has p-value of 0.3. Well, that suggests that the null hypothesis of that the model fits the data well is not rejected, and we therefore have the confidence moving forward that the fit of this initial model is reasonable. So remember that we don't want this test to be significant. I think that's a kind of different from the other test. And this test is not presently can in R, and you can. I think we have some recommendations for doing goodness fit test in other
This is a
software.
funny story because, so Kelly Archer wrote this, this was a dissertation chapter. So like I said, a lot of this stuff comes about where people are saying, there's a particular test that needs to be adapted to the complex sampling setting. And so working under Lemishow, Kelly Archer wrote this and said, here's how we should correct that Hosmer-Lemishow test. The state eventually implemented it in this ESTAT-GOF. And so people started using it, et cetera. And then people started whining online to Bloomleaf. They were like, hey, how come the survey package doesn't have this Archer and Lemishow goodness fit test? And Bloomleaf basically replied and said, program it yourself. He's again a one-man band when it comes to the survey package. He basically said, the paper's out there, you want to add it, write it up yourself. And so people have tried to write various variations of it online, but it's not built into any of the R packages at this point. So yeah, we'll talk about alternatives, but right, there's no ESTAT-GOF that's immediately available for SPY-GOF. The reason is because logistic regression for which this was implemented is just one of the types of models that SPY-GOF is. So he can't write a general purpose goodness of fit function for that function because it's a call to a particular model within that function. So and there's this methodology has only been adapted to logistic regression. So there were some humorous exchanges online about that. You can actually Google for it. See some of the stuff that Lumi has written. But yeah, there's some stuff out there you can look up. Yeah. It's not readily proven. Another thing that came up, I forget who asked about this. I forget who asked about it online, but ESTAT-GOF for this test does not work when you're using sub. Okay, some of you may have run into that or encountered that. To get around that, you have to use the conditional analysis, which, as we've said ad nauseum, is not correct. But it's a workaround for how to get around this error message if you're dealing with a submodel. The thing you have to do first is make sure that when you use that if modification of the logistic model, that your results are exactly the same. So you're not losing anything, you're not deleting any clusters or any straight up by using if. You're seeing the exact same point estimates, exact same standard errors. In other words, you're getting lucky. Just make sure before you use that workaround that you're seeing the exact same results. Just go like before you use ESTAT-GOF. So just remember that if you're using subpop for your SPY logit model, ESTAT-GOF won't work. You have to use if and make sure that the results are exactly the same. It's a subtle issue that has to do with linearization of the way that the Archer-Lemishow test is working, but it's just a workaround. The other workaround is use reformation because this issue is no longer relevant.
Yes. So this is not available in R, but you can program it yourself. And I didn't show the code for fitting a probit or complementary log-log models in R. So here is a way if you want to fit the model with another link function. So you can just change your link functions, the specification here, change the logic to probit, change it to C log-log to fit the probit model or complementary log-log model. And Stata, I think, offers some easy to use post-estimation commands for calculation plotting of marginal predicted probabilities based on fitting model. I don't know how to do that in R at least. And this calculation, it computes a model-based predicted probability for everyone in the data set, as if they all belong to the same subgroup and average predictions. And one can plot marginal probabilities for different subgroups or average marginal effect. That is the expected changes in predicted probabilities associated with 1 unit increase in a given predictor. So it's better to show you like this, this plot. So yes. So Brady, if you wanna.
Yeah, so this is kind of weird how Stata does this, but like, John, shall we go back to the previous slide?
Mhm.
When you calculate a prediction using margins, Stata literally sets everybody in the data set to be in the same group. So suppose that everybody was a male, or suppose everybody was a female, or suppose somebody was an 80-year-old male, or whatever the marginal prediction is that you're computing. Stata sets everybody to that same group and then calculates predicted probabilities, taking all their other covariates as is. So that's how you're marginalizing over all the values of the other covariates when computing these predictions. So you get these average predicted probabilities as if everybody had belonged to that particular group. Those are the point estimates that are being plotted, but then you have to take the variances of those predicted probabilities, and Stata does that using a variation of linearization to calculate those confidence intervals for these predictions. So the really cool thing is that just on the next slide, with just a single command, you can both calculate those marginal predictions and their standard errors, and then plot them in a really nice plot that you can edit or modify, whatever, to visualize the relationships of these predictors with a particular outcome. So like in this model that Youngcha has up right now, the dependent variable is MBE. And the two predictors are alcohol dependence and 4 categories of age, both categorical. After fitting that model, you can run margins, type the name of the predictor that you want to see marginal predictions for, and then you can, if you have an interaction, you can calculate those separately for different levels of the other variable. Called the interaction, that's what's by doing in this, that's what by is doing in this case. We don't have an interaction specified here, but this is how you would get at that kind of plot. And then after you see that table of margins, those marginal predictions, all you have to type is the command margins plot. And Stata will create that plot that you see. Literally just 2 commands to get marginal predicted probabilities based on the fit of a model. So this is incredibly easy and incredibly useful for visualizing the fit of a logistic regression model or many other kinds of models in Stata, because you're getting a plot of predicted probabilities for each of these groups. So this plot shows alcohol dependence has a huge impact on the predicted probability of a major depressive episode. And there's a pretty constant gap between the different age categories in terms of those probabilities. And you see 95% confidence intervals for each of those predicted probabilities, which is a huge added feature because now you're seeing the uncertainty associated with the complex sample design. Literally 2 words to generate this plot. Now there's a package called margins within R that over the years, Leeper, he's the author, he's tried to adapt that to complex sampling settings. He's not quite there yet. He's aware of this. He's aware of what margins can do with this data. It's kind of a work in progress, but eventually, hopefully, he'll get there for those of you who are R users. But you can do some of this, minus the confidence intervals, really, within the margins package within R, but nothing matches what Stata does in terms of these post-estimation plots, to my knowledge, at this point in time, in terms of the ease of generating these kinds of plots. These are super useful, again, if you have interaction. As we've talked about, it's hard to interpret interaction coefficients, but nothing works as well as the graph to make sense of how relationships are changing across groups. Stata makes it super easy to generate these plots. So very, very nice feature of Stata. This is the only place I'll do this. If I have to visualize the physical model or something like that. So those of you using regression models for your final projects, this is a great way to visualize relationships that you're finding and talk about. For sure. Like here, right, we're not seeing an interaction. No, you're seeing an effect of age, you're seeing an effect of alcohol dependence, but that's to be expected because the model doesn't have an interaction, right? We just included the predictors by themselves. So we're not surprised by the appearance of that plot, but if you did have an interaction, it was significant, those lines might cross with each other, might have different patterns, etc. But you can at least visualize it rather than getting bogged down by trying to interpret the coefficients. So very useful for looking at models. So I would highly recommend the use of these plots, especially if you're using logistic.
Well, looking at this figure, I can imagine you're gonna be very proficient in R to program this.
Yeah.
So, well, don't worry if you use data.
Right, so notice the difference on the y-axis. The previous plot, it was looking at the predicted probabilities of a major depressive episode. Okay? This plot is looking at the predicted marginal effects on the probability of this outcome. So this is a different dependent variable. This is arthritis, the probability of having arthritis. And this particular regression model was looking at the relationship of age, gender, and education with arthritis. Now, what this person wanted to plot were the effects of having high school education on the probability of having arthritis. So that was the relationship of interest. What is the relationship of education with the probability of having arthritis? So what's being plotted here in this plot are predictions of that effect. That effect represents the difference in the predicted probabilities of arthritis for high school education relative to the reference category. So that's what each point is. It's literally a difference in the marginal predicted probabilities for high school education relative to the reference category. So what you see for both males and females is that those changes in the predicted probability of arthritis associated with high school education are significant, because none of those confidence intervals for these effects, well, some of them are close to zero, but none of them overlap on the y-axis. So for both males and females, if you have high school education as opposed to whatever the reference category was in this model, you're seeing a non-negligible effect on the probability of arthritis, and those are positive changes in the predicted probability of arthritis. For the biggest change is if you look at males who are age 70, if you had high school education, your predicted probability of arthritis was going to go up by about 0.1 in expectation. There's about a 10 percentage point increase in the predicted probability of arthritis. Not as strong for females, which looks like those effects are basically cut in half compared to what they are for males. But this kind of plot, if you like thinking in terms of changes in predicted probabilities, this can be really useful. And note the change in the syntax. We're using dy dx to plot the change that you're interested in. Okay, that's what's different about this particular syntax. So we want to look at the change in the predicted probability for that particular predictor, the second category of education category. And we want to look at those changes in predictions separately by males. And we want to plot them at these specified values of age. That's what that at option. So it's saying for a continuous predictor, I want to look at these predictions at k age equal to 50, 60, 70, 80, 90. That's what that 10 in parentheses means. It means go up by 10 for every possible value between 50 and 90. So that's how you can play with, what values of continuous predictors you want to see plotted here by using that add option as well within the margins. And again, once you generate those marginal effects in this case, all you have to do is type margins plot, and Stata will create this plot that shows the marginal effects with their 95% confidence. So if you prefer to think of things in terms of effects, changes in probabilities, this would be the plot that you might be looking for. If you just want to plot the predicted probabilities as they are, the previous plot, and the previous slide is what you want to use. Two different approaches to interpreting the same kind of both incredibly useful, and the fact that you can calculate these 95% confidence intervals very useful. So just depending on the kind of approach you want to take to visualizing your results, either of these plots really. Again, they can be applied to many different kinds of models, not just logistic regression, linear regression, other generalized linear models. use margins for a number. So, and if any of you play around with this for your final project, I'm more than happy to walk you through like what the syntax should look like to create these kinds of plots depending on what you find in your model, especially again for interactions. Like this one here is showing, if you think hard enough about it, this one is showing an interaction between education and gender, right? Because those intervals for the marginal effects are not overlapping, males and females. The effects of education are larger for males than they are for females. So this plot is kind of showing that as well, in addition to these general effects of education. There's a lot you can glean from this one plot, depending on the model. Any questions about that syntax on this slide or on the previous slide, or the way that this is working? This is arguably my favorite thing this data does, to be honest. Like these marginal plots.
That's why you put it here.
Hey, Jupiter has it. When Steve, Pat, and I were like, what should we put on the cover of this entire monstrosity of a book? We were like, what's our favorite thing this data does? That's how that got bumped up to the cover. I honestly think it's the coolest thing this data does.
Well, Brady, can you please explain again the dydx in the syntax?
Yeah, dy dx, that's referring to the specific coefficient where you want to see a 1 unit change. The dy dx is kind of funky syntax. It's like referring to a derivative, like a first order derivative, but it's asking to see the change in that predictor. That's the change that you want to plot. So you would put in that dy dx function, suppose that you wanted to see the effects of age, maybe for these different categories, you would put dy dx kh. And that would show you predicted effects of age for all the different categories of gender, and maybe some other categorical variable, whatever the case may be. You would just change that to the continuous predictor. Here, we're picking out one of the indicator variables for education that was included in the model, and we want to see the effects corresponding to that one. So dy dx is the variable where you want to look at the impact of a change in that predictor on the predicted probability.
Thank you.
And you can read this data help for more details about all these options, but we're just highlighting the most important options. Other questions about these two plots within this data? Okay, so again, reach out if you need help or you want to walk through the creation of these plots. I'm more than happy to help you out with that after you finish your models.
Okay, so I think I don't know why this is larger, but this is
yeah. So this is not like what I was getting at. So in this model, ALD we treated it like it was continuous because it was already a binary variable. So it wasn't necessarily the level that was created by Stata for an IDOT variable. ALD was already in the model just by itself. So assume it's continuous. This is how you would get those marginal effects of ALD separately for each age category. So again, for visualizing an interaction, if you look at category 3 of age in this particular plot, for category 3 of age, if you had alcohol dependence, what does that point say? It looks like your probability of MPE is going to go up by about 0.23. That's the effect of alcohol dependence for that middle-aged group. On the other hand, if you're 60 and above, which is category 4, and you have alcohol dependence, it looks like your predicted probability is going to go up by about 0.13. So the relationship of alcohol dependence is not as strong for older ages as it is for middle ages. Again, this is showing you marginal effects. Right? So this is the change in the predicted probability of due to alcohol dependence separately for each stage. So again, a lot of insight based on a fitted model, just with these two very simple.
all right.
Questions about this?
Any questions?
The way dydx is working. This is again like any software, you just have to play with it. Play with these options, fit your model, play with these options, see what you generate. And again, I'm happy to walk you through how to generate this kind of plot. And in Stata, you can customize these plots too. Like you can turn on the graph editor, change the colors, change the line type, change the legends, all this kind of stuff. You can add it all in.
So I got a question about the type of the variable in the dydx syntax. So does it matter if it's continuous or categorical?
Doesn't matter. It's always going to focus on a 1 unit change. So like with ALD, you're talking about changing from 0 to 1, right? It's just an indicator of having alcohol dependence. If I had put age in there and age was continuous, it would be talking about the effect of a 1 unit change in age. It's like it's like a derivative. It's a 1 unit change in that particular variable. That's what's being applied. I almost would have preferred they use the option of like change or something like that. UIDX is a little bit strange, but that's what it's looking for.
Thank you.
Other questions about this?
Okay, well, I think this is the last slide of today's lecture. Well, hopefully, I didn't make you bored.
You should get it on camera. Yes, so we'll bring it back for another lecture a little bit. But no, this was excellent, Joe. This is good. So, I mean, logistic regression is arguably like the most common multivariable modeling technique that people use with survey data. So it's an important thing, and it's important to again play around with these procedures and see how they work. So, but yeah, for those of you using logistic regression, definitely keep both. So, working with 5 will give you a chance to that. Okay. All right, any general questions about concept software here? Anything else related to logistic regression? Okay, I think we're all set. So maybe next time, sure. Yeah. Think about it, send an email. So yeah, Wednesday, we're gonna walk through the lab. So we'll walk through how to do all this in the lab. And then again, no class on Friday. Okay, all right, and we're all set, everybody.
I got this right away.
I should put a speed. Number of specific
Yeah.